Hi, I'm Dr. Alexander NGENZI from University of Rwanda College of Science and Technology, Department of Computer and Software Engineering. So those are the presentation. There are also some of the presentation. For example, if you have to use, for example, the modem. Modulation and demodulation are compatible. We all use modem in our internet connection, and that is simply to say modulation and demodulation. So I hope you understand what is each and every stage of ADC. Now we are going to continue about explaining how signals can be transformed. The analog signals can be transformed into numbers, into digits. For example, remember we talked about the zeros and one. In most of electronic circuits, we say when this can be off and this is going to be on. And in this case, we are going to take an example of digital analog, to analog modulation, which is called an example of it. For instance, we take modem, which we use for internet, remember? So modem is going to be divided into two portions. So one is going to be modulator, another one is going to be demodulator. So what does it mean? So it's going to convert, for example, it's an electronic device. It's an electronic device that makes a transmission of data from a computer or via you can use. So you can have your computer, then you go via telephone, or other communication lines. So suppose if you have your computer, remember our computer is a purely digital device. And some of the telephone, it can be analog or digital, but the mobile phones, most of the mobile phones are purely digitized. So suppose if you want to connect the device, it has to be modulated, and we're using a modulator. What do we mean by modulator in this case? We want our signal to be purely free from noise, interference, crosstalks, distortions, and so on and so forth. So we modulate the signal. Okay, this has nothing to do with digital, but you have to understand the principles, the tips of how you get this. You modulate the signal. Why do we need modulation? We want our signal to be purely free from noise, crosstalks, distortion, and interferences. So we move this one. It's like taking the analog signal, digital signal, analog signal into digital signal. So, and this one also still applies. So you are trying to convert them using a modem. So you have a modulator and demodulator at the end. One of example is a modem. But also you can consider the satellite, the way how satellite, there is uplink and downlink. Remember, if we are trying to understand the concept, for example, if that one is outside from this topic, if you want to understand the way how internet, the computers are connected, which is so-called internet, some of the signals can be connected in the space using satellite. And how does it go? It goes, if I'm introducing the digital communication subject, I have to show this also, so that the students can understand. So here we are trying to. So suppose if you upload any file, we all need uploading and downloading, for example, in this case. So so you are at the earth. This is a person, or you have a computer. This side, you have a computer. or any device, then you want to upload your signal into the satellite system here. So it will undergo some of the conversion, as I said, from ADC to DSC, from to DSC, and then by using the modem this side, modem, then you can easily again retrain your information in this case. So this is the same way as we are talking here. You can have some of the numbers, you upload them, they undergo, suppose if you are uploading some of the images here, the images, they have to go, and then this is download. You download a purely digitized signal. Download it's in normal case it is called downlink or uplink. Downlink or uplink. So where you can upload your file, you can use what we call downlinking. So in this case, we call it in this way. So you can easily obtain your numbers using this and using these systems, so that the data transmission can be changed into analog, or from analog to digital form. So the modem is one of the examples that we use in this case. You can have data and audio images, you digitize them, then you remember when you are digitizing the images or pixels of any picture or image, is going to undergo the encoder, then you come up with you decode it, then you can have your normal picture as you want. So in this case, you can do anything on any signal, be it a video signal, be it an image signal, or what. Nowadays technologies we can use, we use machine learning or some image processing to turn the image to any value that you want. So the technology has made it easier for this, because before it was not there, but this time it's going to be easier, because there is artificial intelligence and machine learning, which is going to make your work easier. So DSP was the foundation of all these things. So it applies, of course, the technologies of DSP, but in this case we don't call it DSP, you can call it image processing. There was a signal processing, of course they are signal processing, they are using the signal processor, and so on and so forth. So in this case, if you are trying to convert the signal, in this case, you can have a signal in its data stream that is purely, for example, analog, for example. Then it goes like this in this way. And you can divide it into intervals, for example, in this way. So you can see it is divided into many intervals here. And this case, there is, there is, you can call this one a peak value, or the value which is overloaded. For example, if you have to analyze overloaded signal, that goes the other one, and this one is unloaded, it's going to be down. The signal is going to be down. So you can just try to minimize it and do it in the same way, but being digitized. So it's going to be in this form. Going to be this form. in this form. So it's going to be digitized in this way. So at any value. So you can see here I'm trying to sample it out with some of the intervals here, there, and there. So the signal can be sampled by using different systems, for example. So here you can take an interval like this, then you try to sample it out in this way, then it goes in that way. Then it is going to show some of the intervals that has been sampled clearly in discrete form. Remember, we are trying to remove this noise into a sampling system. Then we remove all these things, we remain with some of the digital numbers. Yeah, so we have a free, for example, if there is any sampling, sampling system says, for example, by using Nyquist, for example, the Nyquist sampling system, he summarized some of the, it is called the sampling theorem, which used to remove some of this noise, and it was invented by a scientist, which was called Nyquist. So he's called Harry Nyquist, and Shannon. Shannon, remember, he invented what we call the Hamming codes. So it's called the Harry Nyquist. And this is called the Nyquist theorem or sampling theorem. Sampling theorem. So it was invented by this one, and with his friend called French people, the French scientist called Shannon. So they talked about some of the sampling systems, but one of the very critical system was that the frequency, the modulated frequency, is less than, should be less than 2 times of the normal frequency. So they say they mentioned it, and then their sample, which means the rate of the frequency component can be less than the 2 times the normal of frequency. In this case, you can easily determine. So you say it is frequency at maximum is going to be greater than 2 times when it is sampled at the sampling at any time. They are going to be it is going to be greater or equal to the 2 times maximum frequency F max. So this is their findings, what they found, which means the sample at the maximum level is twice the normal some of these sine waves. So we can use ADC to convert all these signals, and we will easily maintain the same size as I showed you from the beginning. So you can use the amplitude by using sample at any value. We went to sinusoidal wave or cosine waves, and so on and so forth. So those were the explaining, a very brief explanation of a sine wave. So now let us begin with a very important thing here, which is going to be used in your tutorials. For example, calculating some of the numbers here. Which is reflecting what we said from the beginning. Remember, we talked about the discrete signal, discrete time signal, and so on and so forth. So we are going to show the presentation of how you can present in 2 numbers. For example, we begin with fractional representation. Number 1. So we are going to discuss about the discrete This is our subtopic, discrete time signal presentation. And number one is going to be functional representation. In terms of function, how do you present the signal in a function wise? So functional representation. So suppose if we have a discrete time signal presented like in this way, which may be in form of numbers. For example, here you can have at function 2, and you have where n is equal to 1 to 4, for example. Also at the function 1, we have n equal to 3, 5, for example, and 0, when function is 0, it is 0 elsewhere. So without doing this value, the elsewhere is going to be, your function is going to be 0. So suppose if you are given this number, and you want, for example, any presentation, okay, this is a function presentation. So whenever you are given this one, remember you are presenting your signal into functional presentation, and it can be present. For example, the output can be x of n is going to be starting from 0, of course, and 2, 0, then 1, function 1, 2, 1, and 0, so on. It goes like this. It goes on repeating like that. So you can present it in that way. So this is what we call functional presentation. So interpreting this, the above one, you can get x of n, which is equal to that function. So it's going to be like this. So this arrow shows the start of the function, which is going to be 0 elsewhere, and the other numbers are going to repeat. So this is an example of a functional presentation of any value. Suppose it is in a discrete form. So if you have this value, you can interpret it. So I can say, given this number, how do you present it in a functional form? You can just do it, or you can do it in the other way around. Okay, so we are at number 2. We said there is a way how you can present your signal. First of all, we say it is a functional presentation, which I have showed you, and this one also, it can be what we call sequential or sequence presentation. So, and this one is a sequence. You can have number of samples over the discrete time signals, which is presented by x of n. So you divide them into sequences. So you can have number of sequences, for example, beginning at negative n, 2 or 0, or 1, 2, 5, 3, 7, in this way. So it can be presented in any sequence. So, okay, just show a sequence. 1, 3 like that. So it should be presented in a sequence of number 1, 2, 0, 1, 3, 4, 5, 7, for example. And then we have discrete value, for example, starting from -1, for example, 0, because there's no 0, 0, can have any value here, can have -1, so on, so on, so forth. So this is what we call sequence presentation. We can also have tabular presentation. Tabular presentation. Which of course is going to be in tables. So it can be, for example, say any value, for example, can be x of n divided by, or for example, any impulse response, as we shall see. Then you draw some of the tables here, you put some of the values. For example, any value can be, okay, you can get, for example, value 1, 1, 2, 1, 2, 3, 1, 1, before. Then you plot some of the tables here, then with which value you want to put in value. So 1, okay, x of n, then should be there, then x of n should be there, then you supply some of the values. So 1 is at the x-axis, and another one is in the horizontal axis, because one of the values here, so it may be 2, 1, 2, 1, like that. So it depends. So one of the value can go there. This is what we call the tabular presentation of the signal, of discrete signal. So another presentation is graphical presentation, and this also is very common. Tabular and graphical presentation are very, very common. So you can have some of the values, then you present it in this form, because remember the discrete value is going to present. You can see, for example, you say if it is a signal like this, you can go like this, for example. It depends. And also here you can have some of the signals. This is what we call graphical presentation. You can also have some values here presented in a negative side there, so and so forth. So this is a negative side that is shifting to the left, or to the left, and then shifting to the right. So you can shift some of the numbers here, and then numbers shifted this side, and then the other one, as we shall be seeing. This is called graphical representation. Yeah. So we have seen how DSP can be presented, but also we have some of the types of how these signals can be presented. Like for example, if you want to talk about the unit impulse, that is unit means number 1. Graphically it can be presented in this way, or sequentially it can be presented in this way. When it is shifted, it is going to be presented in that way. So it differs. It depends on how you want to shift your signal. For example, here you want to show your signal. So now we are dealing with examples, the way how this signal presentation can be given according to their types. Here we can have unit impulse or unit signal, number 1, unit signal. there's unit impulse, there's what, so on and so forth. So unit, you remember when it is unit, it means 1. So if it is a unit signal, you can, for example, it is a unit signal, it's going to be all at 1. This is number 1, and this is 1, this is from 0. So all signals are going to be at 1. Are going to be equal depending to how many signals. And this one is going to be a unit signal, a unit step signal. Unit step can look like that. So they are going to be all at this level. And delayed shift or unit impulse signal, the unit impulse or unit step sample is going to be a unit impulse can be shown if it is going to show the function. For example, impulse signals is shown in this way. Of A, of course, it's going to be in this way. So it is going to be 0 whenever n is not 0, and it's going to be 1 when n is equal to 0. So this is a signal that's going to have a unit step impulse that's going to step in this way, and the normal signals are going to be in this way. So it can be in negative side like that. So a function can be shown in that way. But the unit the unit shift, the delayed shift, if we want to delay or shift something, it's going to be it's going to have some shift there, and then of course it's going to be shifting also. For example, if you have a figure like this one, it's fine. So it's going to shift from 0 to any value, call it 3. So n minus 3, for example, is going to shift up to 3 here. So the signal is going to appear here. So it has shifted. So it is called delayed unit step. Delayed unit. Can call it step or unit sample. So you can call it delayed impulse. So unit sample, delayed impulse signal, which is called also the unit sample. So you can delay any unit like that. So it depends. If it is delayed unit, you can call it n-1, which has delayed from the signal from 0 to 1. That is a unit that has been delayed. And in this case, it's going to unit impulse of n is going to be no, of course here we have to show that something has been shifted, which is okay. It's going to show that any has been shifted to any value, which may be 0. The function may be 0, but here n is equal or is different from the shifted number, and can be 1 when of course there is any shift n is equal to any shifted number. So this is very common to this delay function. And also you can have delay shifted unit sequences. You can have a sequence of numbers shifted from one side. So it can be, for example, delayed shifted unit step. Sequence, which may be, for example, it has been delayed, but for a certain unit, for any shifted value, which is 1, it will be 1 when n is equal to k, and 0 when n is less than k, the shifted value. So the value here can be shifted, for example, in this case, and it can be like this. So okay, some numbers have been shifted as an empty state, but here you can see that some of the group numbers can be shifted. So it's going to be any shift of n minus k, of course here. And here we can shift here any value whenever you want. So this is what we call a delayed or shifted unit step. So these values will be shown once you are trying to draw some of these diagrams presentation, so that you can interpret your discrete time signal easily. So you given any number of signal, you can come up with a value. For example, there is also what we call, there is a unit step, there is a unit impulse, but also there is what we call ramp signal or ramp impulse. So the presentation of a ramp signal. Remember, a ramp signal is the signal that moves like this way. Remember, in your so it goes in that way. So it can be the signal. The signal can be, of course, can go and can have some of the numbers shown this way. So in that way. So suppose this is the time, this is amplitude, for example. So for any given value here and the other one, so it can go to this. So this is not very important. Here, so it can be moved this way. So this is what we call a ramp signal, presentation of discrete value, and this ramp signal can be presented by n or given to the value, the function may be n when n is less or equal to 0, and also it can be 0 when n is greater than 0. So this is a functional presentation of a ramp signal. So discrete ramp signal, for example. Ramp signal. So it can be presented this way. So here can be numbers from 0, 1, 2, 3, 4, like that, any value, and here can be presented in a different way. So here can be unit, can be 1, 2, 3, 4, like that. So here also can be the same. So this is what we call a lamp, and the lamp is perpendicular to, it has to go to it's like a signal that goes from the center perpendicular to the XY axis. So The unit, there is also, lamp also can have a unit in shifty, it can have also a unit impulse in the same way. So you can also have a value of n minus n value here, k. So in that case, it will shift, for example, into a given value when, for example, it should be n is different to k, and some value when n is equal to 0 when n is equal to k. The same way as you have seen. And that one can shift. So this value can shift to the other side. For example, here you can draw a same way like this, and you will have some shifted lamp at this side. You see, from this point to this point, it has shifted to these values. So it goes to the other side. And here, of course, the main arm, and it shows some of the signal that has been shifted. Yeah, so this is a lamp, but also you can present it in an exponential signal. So signals can maybe unit step, maybe unit impulse, can be ramp signal, maybe exponential signal. Then depending to the nature, the way how they behave is the way how we have to present them. So remember, it depends. So using your basics in mathematics, you know, when you have XY graph, the exponential signal will move like this way. So it's going to move like this way. So you can also draw this signal presentation. You can have this one with this one. So the same way, you can go in that way. So this is what we call exponential signal. So we call it exponential signal. So it is exponential signal, which can be presented in this way. So you have your xy axis and the value. So in a function form, remember, when it is exponential, x of n is going to be a in 2 power n for all values of n, where a is a real number. So for all values of n, so it will look in that way. So the exponential value also can be shifted to this way or the other way around. So the other one is the right way. It can also be shifted in the left way, where once it is having some of the shifted side. So there is also sinusoidal discrete time signal. So this is a signal presentation of discrete time signals. So I'm teaching the way how you can remember sinusoidal signal goes. Okay. Sinusoidal signal. So you remember it goes like wandering this way, like this is the sinusoidal signal. So at this level, for example, if you have 10 frequencies like this, okay, 10, then it can be this in this way. Goes in this way, like that, and then the output can be, for example, if you have this one, you can have so it will be like this. course like this, and then for example like this, and then to the other side also can be like this. And then it goes like that. And so on and so forth. So in this way. So this is sinusoidal presentation. Remember, the sinusoidal representation of any given value is going to be the sine of anything, 2 pi, for example, 2 pi t, like that. But it has to be, for example, any value here. So yeah, so that is how you can present it in discrete time signals. So these are the signal presentation. You can also move to other presentation. For example, it may be not always that this discrete signal can be unit cell. It can also lie into zeros here, then it goes to that, then it goes to that. So it will depend. You can begin with zeros here or empty space, then it begins like that, but depending on the number of shifts. So we have seen how you can present the signal. But now, what are the expressions? We have seen some of the basic expressions when you say time in discrete form like this one. Or when it is shifted, for example, this signal presented actually shifted by k values. So the shift form. And you know, for example, some of the normal expression, for example, if you say negative infinity to infinity like that, so all those are normal in our presentation. So, but the general expression of discrete form or format, discrete signal, okay. Now I have to change the subtitle of our topic and just show.